Hello, this is a video about separation of variables. I'm going to show you two examples of differential equations where this technique applies. So this one and then I might say a few words about when this technique applies in general. So let's just kick off and throw ourselves at this equation here. Now the trick is first to rewrite it a little bit, and I multiply both sides by y. So I get y equals dy dx equals minus x. And now I'm going to do something that's generally a little bit forbidden, because I'm going to multiply by dx. Now that in a sense is not allowed, right? Because dy dx is not a real fraction. However, what I'm going to do now can be theoretically justified, so I'm just going to go ahead and do it. So what do we get? Well, if you do that, you get y dy equals minus x dx. Now, this really doesn't make sense, does it? But it does as soon as I integrate at both sides. Now, the step from here to there can be theoretically justified. It's not part of this video, but now we are okay. And the nice thing is, now we've changed our differential equation into a problem where we just have to integrate two sides of the equation. So let's go ahead. Here we integrate with respect to y. That's what the dy wants to say. So I get 1/2 times y squared. And on the other side, I get minus 1/2 times x squared. Now I need an integration constant. I can put one there and I can put one there, like a c here and a d there. But since they're both sort of random constants, I might as well put just one on one side, right? So I choose to put it here. You can put it there as well, I don't mind. So this is it, and we're almost done. So actually, implicitly, we have solutions of our differential equation now. But you might want to write it as an explicit function. Y is an explicit function of x, for example. Now, so I could multiply by 2 to get y squared equals minus x squared plus 2c. And there's one more thing to be said here. C was sort of a random constant, so 2c is the same in a sense. It's still a random constant. And what people do, which is again sort of fishy, however, it's okay that people don't put the 2 here. They don't put it. They say, okay, c is actually a new constant here, but it's still a random one. So algebraically this doesn't make sense, but it does have meaning in the sense that this is still a random constant. It's just twice the constant we had there. So there's some funny things here. Now, of course, we could go two ways here. Actually, I would like to show you first this. I could rewrite this as x squared plus y squared equals c. And then, of course, we see very nicely, this is the equation for a circle. I hope you recognize it. And that's sort of an implicit function, right? So the other way, what I could do is, of course, I could take a square root on both sides, and then I get y equals plus or minus the square root of, and let's write it a little bit, c minus x squared. And this basically splits it into the top half of the circle with a plus and the bottom half of the circle below the x-axis. Now, if I go back and I look at this equation, there's actually a subtlety, because since we divide by y here in the equation itself, actually we should demand that y not equals 0. So if I say half a circle here, I really mean without the endpoints on the x-axis, and the same there. And this equation only holds for y not equals 0 if I compare it to the differential equation, if I really want solutions of that equation. So that's the subtlety. Now this is my first example. So what we did is we rewrote it so that everything with a y was on the one side, everything with the x was on the other side, and then we integrated simply. Now generally this works if you can rewrite your differential equation to the shape fx times dy dx equals gy for some functions f or g. In this case, f, excuse me, this should be a y and this should be an x. And so f of y simply was y here, and g of x simply was a minus x. So, and then in general, what you would do is rewrite this as f of y dy integral equals the integral of g of x dx. All right, so this is the general technique that we apply, and then we integrate and hopefully find a good implicit or explicit description of the function. Now, up for a more difficult case, first of all, it's not immediately clear how to rewrite it like this, because notice there's sort of a multiplication here. So a multiplication of everything with y times this should be g of x, but here the terms are still mixed. I got x to the cube times y. So the first step here would be to rewrite it and to decompose it a little bit. I can actually decompose with 2y, and I get 2x to the cubed plus 1. Okay, now I have a multiplication here, that's good, and I have to take these terms with y to the other side. So I can rewrite this now as 1 over 2y dy dx equals 2x to the cube plus 1. Now I have to be careful here, because just like before, actually here now I have an equation where I divide by y, so it's not entirely equivalent to this original equation. Actually, I'm throwing away one solution, so let's check if y equals 0 is a solution. Well, if I plug it in, then the right-hand side is completely 0, and indeed the function, the derivative of the function y equals 0 is also 0, so actually I should take care that y equals 0 is a solution that I have as well. So a solution of this is either a solution of that, or it is the solution y equals 0. It's easy to forget about that one, so don't do it. Now, let's continue where we want to be, because we can write this as I take the half outside of the integration. I get 1 over y dy equals the integral 2x to the cube plus 1 dx. Okay, so far so good. I know how to integrate 1 over y, or find an antiderivative if you want. It's ln of the absolute value of y. And here, of course, I can do it too. It is 1/2 of x to the 4th plus x, plus I put my integration constant here. Again, now we have an implicit function for y, of description of y, and we could try to make it more explicit. So first I maybe multiply by 2, and I get the ln of y absolute equals x to the 4th plus 2x, and here's the silly constant trick again, I just don't put the 2 there. Now I take exponentials on both sides, so notice here it's not anymore really about solving the differential equation. It's more algebra in a sense, but okay, let's do it. So I get the absolute value of y equals e to the power x to the power 4 plus 2x plus the constant. And now there's a little subtle reasoning about exactly what y can be. Remember, actually all this time we also had the option of y to be 0. Now, if I want to get rid of the absolute value sign, if y absolute is this something positive, then y actually could be plus or minus that. So I get y equals plus or minus e to the power x to the power 4 plus 2x. Well, and then I could use my rules for exponentials. It says times e to the power c. Now, e to the power of c is, of course, this thing is positive generally. it's still a sort of random constant, but it's positive. But here is we have solutions with a plus and we have solution with a minus. So actually we have a whole range with positive constants and we have a whole range, if we take the minus, with negative constants. However, we also have the solution y equals 0. So if I add that, that means that I could also multiply with a constant 0. So actually the whole range of solutions would be c times e to the power x to the 4th plus 2x, where c can be any real number. So this last line sort of summarizes the solutions for plus and minus here with a positive constant there, and the solution that we found here by being very careful. So this is the full story for this differential equation. The technique was the same. We separate the variables in the sense that everything with x on one side, everything with y, x here, y on that side, and then we integrate both sides, and from there on it's basically rewriting in an algebraic way with some good care taken of what happens with these constants. So I hope this helps you with your own separation of variable differential equations. So good luck.